the nature of these molecules to meet the imaging mode that we need, and it does not affect where the capsids go because they're all tucked inside. Okay? The dream of this, then, is that once we can reach a particular target, we can swap in drug molecules. These are two that we've worked with. I'm going to talk about this one in some detail later, but on the right, this is that Taxol molecule again, which is a treatment for breast cancer. And we've shown already that when this is attached on the inside of the shell, we can put about 120 copies in each of these viruses. When they go to a particular cellular target, they're degraded. This releases these Taxol molecules and they kill the cell. So that was a big result for us. It showed us we actually could put synthetic drugs in these carrier shells and we could actually target them to specific places. So I kind of point out at the beginning we chose this virus because of these holes in the structure, these 2 nanometer pores that it has. It has these pores in the shell, and so that kind of limits us to the fact that these all have to be 2 nanometers or smaller in terms of what these cargo molecules were. And so one of the things that took a long time to get past was that limitation, if we want to have larger cargos. I just mentioned briefly some more recent work in the lab. Jeff Glasgow and Stacy Capehart found that you can actually take these capsids, and you can tear them apart using specific sets of conditions, using acetic acid and this molecule here called trimethylammonium oxide. It took a long time to figure this out. But when you do that, this capsid will come apart and form its individual components in solution, and they'll remain in solution under these very specific conditions. And then what Jeff found is that you can put any cargo you want with a high negative charge on it, and what that does is it brings these pieces together around that cargo molecule. Even if it's very large, then the capsid will assemble around the shell, and those cargo molecules are stuck inside. They can't get back out through the holes. So it's sort of like building something on the inside, and then it's trapped in there until the capsid degrades. Just to give you two examples of that, this works great for proteins. It's a major goal